Okay, hello everyone. This is a recording for week 16 discussion questions. There are 5 posted online, so I will go over those. So question number 1 says an object is placed 60 centimeters in front of a 30 centimeter focal length converging lens. Alright. 30 centimeter converging lens. So this is a converging lens. Converging means it's a convex lens. Convex lens is a converging lens. Means it's something like this. Here's the principal axis. We mark F and F on both sides. Converging lens means parallel light goes through a single focal point. This is a converging lens. Alright, what do we know? Object is placed 60 centimeters. D object is 60. F is 30. Convex lenses have positive focal length, right? Focal length is positive. 30. How far is the image of this object from the lens? It's asking DI. So we can use lens equation. It's same as the mirror equation. Oops, sorry. Common denominator 60, so 32 minus 1 over 60 di is also 60 centimeters. Now this, okay, so where's the image? It's just asking how far is the image of this object from the lens, so 60 centimeters. Now let's say how to draw this diagram. So principal axis. Okay, let's undo that. We mark where the lens is and then just put a small convex lens like this. F and F. F is 30. This object is actually on point C, right? Curvature point. 60 centimeters is twice the focal length. So here's the object. And we found out that DI is also 60 centimeters. Now remember, for lenses, a positive distance is on the other side of the lens, other side of the object, right? Lens is something that light travels through it. Mirror is something that it reflects. So for a mirror, if it is in the same side, if the image is in the same side, that means light has reflected and creating an image. That's a positive distance. If you have to extend the lines, that becomes a negative distance. For lenses, light needs to pass through it. Light will pass through it. And if it is creating an image in the other side where the light is actually going to, that's a positive distance. So, and also you can see it is creating an image at the same distance like the object. So this is that particular C curvature point. Even for mirrors, you know that if you place an object on C for a concave mirror, it creates exact image upside down at the same point. So this is the same thing when it comes to lenses, right? So here comes light, goes through this like this, and we can use the one that goes to the center without bending. So somewhere here, this is pretty much going to be the same size image upside down. So what is the distance? 60 centimeters. Positive means on the other side. Can even think about magnification. Negative di over do, negative 60 over positive 60, negative 1. 1 means same size, negative means upside down. Alright? Okay. Alright, let's go to the next question. Question number 2. 10 centimeters, where is the image? Diverging lens. So this is a diverging lens. A concave lens. It's a diverging lens. Remember, when it comes to mirrors, concave is the positive mirror. Convex is the negative mirror. Means convex mirrors makes only one type of images which are virtual. Convex makes variety of images. When it comes to lenses, it's the opposite. Convex lens makes variety of images. Concave lens just one type image. Now here we have a concave lens. So DO 10 cm, F is 4 centimeters. Remember, this is negative. So diverging lens is a concave lens, focal length is negative. That is the image. So let's take 20 as common denominator, negative 5, negative 2, di is negative 20 over 7, yep, which is let me double check just in case. 20 over 7, .85. So di, we have a negative number. For a lens, if we have a negative image distance, that means it's going to be in front of it. And we know that for these lenses, for diverging lenses, that's how the image is going to look like. If it is behind the lens, that's a positive image. So a negative distance means it has to be in front of it, the same side as the object. You are looking at it from here. So here's the object, light comes in, here's the focal point, 4 centimeters, it diverges, appearing like coming from this point, so it goes like this, one that hits the center, goes without bending. Here we have a small, it should be in dotted lines, right, like this, a small upright image. So again, you can find the image properties like magnification, negative di over do, negative 2.85 over 10, that will be 0.285. That's the magnification. It's positive, means it's upright. It's smaller than 1, it's 0.285, so the image is 0.285 times smaller than the object. Number 3, an object is 80 centimeters. So it says object is 80 centimeters in front of it, image 20 centimeters behind the lens. Looks like a convex lens, right? What is lateral magnification? It's just the magnification. When we say lateral magnification, it's that using this equation, di over do. We are not using the height of the object, right? This is also magnification. But since we are using the distances, we call it lateral magnification. So DO is 80, DI is 20, both positive. Asking M. We don't even need to do any math. We can just use the magnification equation. Negative 20 over 80. Negative 1 over 4. Negative 0.25. That is the magnification, right? So negative means upside down, small image. If you want to draw it, you can do that. What's the focal length? Just for our curiosity. 1 over 80 plus 1 over 20 equals 1 over f. 1 plus 4, 1 over f. F equals 80 over 5. 16 centimeters. It's gonna look like this. F and F16. This is 16, so the object gonna be over here. Comes in. Oops. Hold on. Goes through F. And it comes like this. Okay, here's your upside down image. Ideally 4 times smaller. Magnification is 0.25, 1 over 4. Negative upside, so it's upside down. And it's on the other side. This distance is 80 centimeters. This distance is 20 centimeters. Okay. Number 4. Number 4 says DO 15 centimeters. Focal length. This is a convex lens, so positive 20 centimeters. Asking what's the magnification. For that we need to know what is DI. We need to know this. So 1 over 15 plus 1 over DI plus 1 over 20, 1 over DI. I would take 60 as the common. 3, 4. Am I doing this right? Yep, 3. So minus 1 over 60. This is 1 over DI. So DI is 60, negative 60 centimeters. For a lens, if you have a negative number, that means it's in front of it, same as the object. And this is going to be a virtual one, right? Okay, so question is, what's the magnification? Negative DI, negative 60 divided by DO, which is 15. 60 divided by 15, 4, bigger. So it's a convex lens, F and F. is 20, but object is in front of that. That's when it creates this big virtual images. See? Okay. Comes in, goes like that, goes like this, extend till they meet. We are looking at it from here, so we have a big upright virtual image. So if object is 1 centimeter tall, for an example, this is going to be 4 centimeter tall, and magnification is 4. Okay, number 5. Here we have a 2-lens system. An object is placed. So we're going to draw a one long principal axis for both of them. So the first one says focal length is 45. So it's going to be a convex because it's a positive. So here F and F. This is lens 1. F is 45. DO is 90. So object is over here. F is 45, so twice that. So this is again on C, means that upside down same size image. Alright, a length of focal length negative 25 is placed 80 centimeter beyond the first lens. So here's the first one. Second one is 80 centimeters behind that. It's a diverging lens. Second lens, F is negative 25. Now what happens here is, so let's find out where the image is for the first one. For the first lens, we know that it's on the other side. We kind of know where it's going to be. Okay, this problem has an issue. I need to fix that. Alright, so we'll I'll change it after I fix the first part. Alright, this lens needs to be moved a little bit, not 80 centimeters. I think it was 180. Somehow didn't get copied correctly. Okay, so let's find the image of the object. One over 90. centimeters positive, so image is going to be, now this is the first lens, it's going to be 90 centimeters from that on the other side. So let me erase this. Okay, so if this is 90, that image is going to be over here, 90 centimeters from it. We know that it's going to be upside down. We can prove that using magnification. Negative di over do, negative 90 over 90, negative 1. Negative upside down, 1 means same size. So here we have the image. And how this happens? We go the light beams, comes in, goes through F. We can use another one that goes through F. The blue color. to F, goes parallel. So we have the object. Okay. The second lens of focal length negative 25 centimeters is placed 80 centimeters. Let me change this to 100 centimeters. Okay, for the second lens, this and 100 cm behind the first. Okay, all right. So this distance is 90. So second lens is over here, 100 centimeters from the first one. This image 1, it's a real image, right? It's a real image means there's actual light in it. This image becomes the object for the second lens. So for lens 2, DO, what is the DO distance? Image is 90 centimeters from the lens. Between the lens 100 centimeters. So this is the DO for the second lens, which is 100 minus 90, 10 centimeters. Its F is negative 25. So where is, then what happens? So it is like you have this lens and there's an object, just an upside down object 10 centimeters in front of it. So what kind of image that's going to create? So for the second one, let's try 1 over DO plus 1 over DI plus 1 over F, 1 over 10 1 over DI plus negative 1 over 25. 1 over DI, negative 1 over 25 minus 1 over 10. 50 will be a good denominator for both of them. Negative 2, negative 5. So DI is 50 over 7. Negative 50 over 7. 50 over 7. 7 point something. Centimeters. Negative 7.17 centimeters. So that means it is going to make a small image in front of it like this. Where is the image? It's going to be 7.1 centimeters in front of this second lens. Or you can say, okay, so this is 10 centimeters. This gonna be 7.14 centimeters. So how do we draw the ray diagram for this second part? Here's the object. Light comes in. So focal is over here, right? 25. So parallel light diverges such that it comes from its focal point. One that goes to the center goes without bending. Where they meet, here you have a small image. So this is how we work on multiple lens problems. We find the image due to the first one, and that first image becomes the object to the second one, and look for the distance separation between the two lenses. Based on that you can figure out what the object distance for the second one, right? So the first lens creates a positive means a real image. It has to be a real image, and then that real image becomes an object to the second lens. The second one could be even it doesn't need to be a concave, it can be a convex lens, and we might make another real image out of that. This is the principle behind many optical instruments like microscopes and telescopes. They take the first lens, it makes one image, sometimes it magnifies the first image, and then that will get magnified again by the second lens. So in complex microscopes and telescopes, there's multiple lens systems, not just two, but at least they use two lenses to give some magnification. Okay, so we will work on more problems. I will discuss further in class next time when we meet. All right, thanks.